Okay guys, so what we're going to do today is day 2 of content with calculus. Yes, it's day 3 that we're meeting, but it's day 2 of content. Okay? And what we are going to cover today, if I went to my schedule, is going to be right here. So day 3, which is day 2 of content, we're going to cover determining limits using algebraic properties of limits. Okay, so we're going to use laws of limits. Okay, we do have a summer assignment here, a summer quiz, the summer assignment quiz that we're going to take today. And what we will also do today is we're going to determine limits using algebraic manipulation. Just a reminder to use this form at the very top. You have some essential questions as far as what should you be thinking about as we go through this unit, and what should you be understanding as we go through this unit. Okay? Alright, so let's go ahead and begin. With our notes, let me go back over here. Alright. Limit laws. So properties of limits. L, M, C, and K are real numbers. Think of them as constants. And we're going to say that the answer to this limit is L. Okay? And then the answer to this limit, okay, so the answer M is the answer to this limit. What kind of values are L and M? You remember what kind of values are they? They're like numbers, right? They could be like 20. They could be -5. They could be infinity, right? They could also be does not exist. Remember that? We talked about that with graphs and whatnot. So, what these are saying is that we have 7 rules that we can apply to limits. We can apply these rules when limits are adding with each other, subtracting with each other, hence sum and difference. We can do it when they're multiplying, which is a product, when they're dividing, which is a quotient. We can even do it when there's a constant that's multiplying with a function called the constant multiple rule. And this one's very powerful throughout this entire year, and you're going to see that quite often. Okay? Alright, so let's start with adding and subtracting limits. Okay? Right here is a big, huge parentheses. And if I asked you to rewrite this using limit laws, what you would show is the following. You would say the limit as x approaches c, maybe it'll let me, maybe it won't. I'll have to write it again. Is going to be applied to both the f of x and the g of x, and then you'll add them then. Okay? What does this feel like? What does this look like of some math that you've done before?
Logs.
It looks like logs? Okay. In what way?
Like if you add them.
If you add them? Okay, so let's look at logs. So if you had a log of x times y, you know it would be the same as if you were adding them like this. Do you agree?
Yes.
Nice. And I like that you guys saw the logs. What else do you kind of see from here that would get you here that you've done in math?
It's like distributed.
It looks like distribution. Okay? Distribution would be taking this and distributing it to both of them. But here's what I'm going to say. Multiplication does not exist there. Okay? So, f of x. F of x. I said of. 9 out of 10 times of means multiplication. Is this one of those times?
No.
No, there's no multiplication. The natural log of x. Does this multiply? No. Okay, that's the same with limits. The limit of f of x, there's no multiplication. The way I want you to say it is you're applying the limits to both functions. Okay? There's no multiplication, you're just applying it to it. So, The answer that we get from this is L. The answer that we get from this is M. So it's basically just adding those answers. And these will look a lot clearer when we look at the example problems with numbers and equations, okay? But I want you to understand it conceptually as well. Guys, the same thing happens for the difference. The only difference is going to be that you're going to be subtracting them. You with me? You're still going to get the L, you're still going to get the M, you're just going to subtract. So this is how you say it. Listen. The rule is this. The limit of the sum is equal to the sum of the limits. The limit of the difference is equal to the difference of the limits. You with me? Now, let's move on to product rule. The product, the limit of the product means multiplication, is going to equal the product between the limits. You see what I'm saying, guys? And that would look like the same thing over here, only I'm going to multiply those numbers. Okay? And the last one is the division. I'm going to end up dividing by whatever those numbers are. Please ask me questions if you have them. The earlier you ask, the clearer everything else after that will be. Okay? Any questions? Yes?
You said something about before log.
Okay.
That it's
So the reason why we brought log up is that this one, logs, when you're multiplying in here, you are adding out here.
Yeah.
But nonetheless, here, there's still no multiplication occurring.
Yeah,
It's
but
not log.
This log doesn't apply to the limits.
Correct. No, this was just an example. You're correct. This has nothing to do with limits. I just wanted to see how you started to interpret what you were seeing with limits. Okay? So we could tie it to previous knowledge that we have. But yeah, you're correct. This is not limits. Okay, so now let's go to number 5. Number 5 is a constant multiple rule. Okay? Remember, K is a constant. It could be 30. It could be -5. It could be pi, which is a constant. You with me? It could also be E. Does anyone know E?
It's like 2.7.
2.718. That's good enough. And it keeps going, right, with other numbers. So those are constants. And I tell my students all the time that a good way to find out what should be seen as a constant. I always tell students A through E, because of this, can be interpreted as constants. Typically, not all the time. F and afterwards can typically be seen as variables. Okay? Now I know K is after F. But they did show us with this that it is going to be a constant. Okay? I hope that helps you with like homework and other stuff as well. Alright, so a constant multiple rule is this, guys. If there is a constant multiplying by a function, what you can do, now imagine, like, let's say this constant is my phone. I can pull the constant out and put it way over here, let's say near the door. And what I can do, now that I pull the constant out, I can evaluate everything else. And guys, once I get this answer, guess what I'm going to do with this K? I'm going to multiply it back in. That's why it's called the constant multiple rule. So I'm going to bring back my phone, aka the K, and I'm going to multiply it back in with whatever I get as an answer from this. Are we good? Okay, and you'll see some of this too as we progress through. Alright, so the power rule with limits, R and S are integers, and it says S cannot equal 0. Why does it say S cannot equal 0? Because we can't divide by 0. It's an extra caveat. It doesn't need to be mentioned if you know that, but it's just an extra reminder you can't divide by 0. And check this out. What you could do is you could pull this out to where, let's just look at this function again, and you would get L as your answer. So the R divided by S almost feels like the constant multiple rule. You're pulling it away from the function, you solve and you get L, and then you bring it back, but you're not going to multiply by R over S. You're going to use it as the power you're going to raise it to. Are y'all with me? So that's the power rule for limits. Questions? Okay, so let's go to the last one is big. The last one's a big one. And most of the time it might be a bonus question, or it might be a piece of a question on a test that separates the 98s from the 100s and stuff like that. Let's look at number 7. This is a limit of a composite function rule. Now, let me give you an example of what this looks like. I think it's easier to show. We get L from this limit. But then we get f of L from this limit. Because we're saying the limit of f of g of x as x approaches c is equivalent to bringing that inside so that you apply the limit to the g first, and then whatever you get, plug it into the function of f. A quick review of composite functions. Quick review. If I have something that looks like this. Okay? Is that a composite function? Is that a function composed of 2 or more functions? Yeah. What's the first function? Let's call it f of x. What could we say f of x equals? 1 over x. What would g of x be? Square root of x. Because this right here that I just showed you is an example of which one? F of g or g of f? Which one is this one equal to? G of f. That means you would take whatever f is, which is right here, and you would plug it into the input of g. So the input of g is right here. So when you plug that in, you get this. Are we good? Okay. So here's the thing. What this is saying is that you can bring that limit inside only if the outermost function is continuous. What does continuous mean? Right.
It just goes on forever.
Okay, so it goes on forever?
No discontinuity.
There's no discontinuity, so there's no breaks. So here's what I'll say. Does a continuous function, let's draw them real quick. I'm going to draw f of x right here, okay? So 1 over x looks like this. That's f of x. G of x looks like this. Does this go on forever and ever? It does. It goes on forever. But is that continuous? Is 1 over x continuous? It's not. So some of our definitions might change a little bit, okay? Does this look like it's a continuous function? It is a continuous function. Because a continuous function does not need to have a domain that is all row numbers. There's a difference between a domain that has all row numbers and continuity. Continuity is this. A continuous function is a graph that you can draw without lifting up your pencil. So what he was saying as far as not being discontinuous, not having a break, that is continuous. That's what that means. So this is a continuous function. Square root of x is a continuous because I can draw that without lifting up my pencil. You with me? But this over here is not a continuous function because look, I just had to lift up my pencil. It's not continuous. Are Are you with me? Okay, so now let's go to this. The outermost function of what we have here is g of x. The outermost function. Is this a continuous function? Yes or no?
Yes.
Yes. So that means if I were to analyze, check this out, if I were to analyze the limit of x approaching c of g of f of x, because of the fact that this outermost limit is a continuous function, I can bring in that limit symbol inside, and I'm going to apply it to f of x first. And whatever I get from that, then I'm going to put it into the g of x function. Are you with me? That's how you're doing this. Let's do it the other way. What if we had f of g of x? The outermost function is f. That's this. Is this continuous? 1 over x is not continuous. It has a break in it. So you could not bring in the limit in this specific example inside. You could not be able to do this because f is not a continuous function. But you can do this because g is a continuous function. I hope that helps. You have to see it with some equations to understand that rule 7. All right. So, with that in mind, let's go ahead and start going to the examples that include numbers, variables, so on and so forth. So, f of x is equal to this. G of x is equal to this. Quick sketches. There's f, here's g. So let's say that here's f, and here's g. Jordy, go ahead and read this for us, please. Perfect. The limit of f of x as x approaches 1. So we're going to look at f of x. This is g of x. Let's approach, guys, together. We're going to approach 1. And we're going to approach 1 from the right and from the left. Remember, we're trying to make that ET moment. Jump on the function. So as we're approaching from the right and from the left on the function, we're still trying to approach this 1. Can someone tell me, what would that y value be? -4. Okay? So that's another way of doing it. And some of you are like, man, that's pretty easy. I could just plug it in. It almost feels like just regular function notation. Okay? So yeah, you can go ahead and put -4. Any questions? Okay, so let's look at B. B is saying the limit of g of x as x approaches 5. Okay? So if I go to g of x and I find 5, okay, so let's do that in black. So this is 5, and I'm going to approach 5 from the right and from the left, and I jump on the function. Can someone tell me what would that y value answer to the limit be? 25. Okay? And this almost feels like too good to be true. Like you're just plugging these in and getting these answers. Now let's do this one. What is special that we just learned about this right here? We're going to do f of x. So this is a composite function, right? This is g of f of x. Another way that you probably would see this would be written like this. G of f of x. Remember that? So you got to ask yourself, is the most outer limit, which is g of x, is g of x what? Continuous. And you tell me, is it? Yes. So that means I could apply limit law number 7, and I could pull into this equation, because g of x is continuous, I can pull the limit inside. And all I'm doing is now is I'm figuring out two answers. Okay? The first thing that I'm going to evaluate is a limit. It's this. And can someone tell me what's the answer to that? -4. We did it in part A. So the second step is not finding a limit, but just finding what is the y value on G at -4. Anyone? 16, right? It will be a positive 16. So the answer to this will be 16. Questions?
So you're just finding G.
Yep, we're just finding G of -4.
So not the limit, just what it is.
Yep. This is a really good, I think he's alluding to it. Let's say on this graph, at -4, there was a hole in the graph. At -4, there was a hole in the graph. Could I have done this to begin with? No, because it's not continuous. Could I have done this if I said restricting from 0 to 5 and only looking at 0 to 5? Could I then use the rule?
Yes.
Yes, because that interval is continuous. Okay? Now, real quick, just a little recap from what we talked about last time. If this did not exist, and you looked at it like G of -4, and there was nothing there, what answer should you put? Undefined. Nice. But what if it was a limit? Does not exist. Those are the two differences. I want to make sure that you are very good with that. Alright, so now let's go to the next one. So, the limit, the sum and difference laws we're about to use at the same time. Alright. I told you that it would look like, it would smell like, it would feel like distribution. But it's not. You're applying the limit to all of the pieces. The first piece that you're applying to is 3x squared. The second piece that you're applying to is 5x. And the last piece that you're applying to is 1.
Would it be -5x?
Yeah, you're going to subtract it, and then you're going to add it.
So you just subtract the actual value of limit. It's not of -5x.
Correct. So guys, this is a good question right here. This negative, Christian is asking, should we put it here or can we bring it out here? And I'm saying you can bring it out here. Let's see, we can see why. Why can I do that? What law did we learn today that says I can pull out that -1? The constant multiple rule. And it makes it easier to see 5x. Go with me? Okay. So now, here we go. I'm going to overkill these first couple with graphs so that the harder ones coming today, you understand, okay? Here you go. This first one is 3x squared. That's a vertical stretch by 3. The next one is a vertical stretch by 5. What does the last one look like? Just a straight line, right? You don't have to raise your hand, just say it out loud. It's just a straight horizontal line at what? At y equals 1, right? Y equals 1. It's a horizontal line. X equals a number is a vertical. Y equals a number is a horizontal. Now look. We are going to approach 2 on all of these. So if I approach 2 from the right and left, what do I get here? What would I get as a final answer for all of that? 12, right? Speak up, guys, please. Don't be shy. If you get it wrong, I promise I will help you. If we approach 2 from the left and right here, what would this give me? 10. How about the last one? 1. Here's a trick that I'll show you right now, guys. This had a something that this did not have. What was it? An x. So the constant multiple rule says I can pull out these constants all day and just leave the x's left in there. Because when you apply the limit and you multiply that constant back in, there's your answer. You with me? Alright, so what's my final answer from all of this? 3. Perfect. There's your answer. And guys, you could have gotten that from your very first step that you should always do when you're doing limits, is direct substitution. You could have just put that here and here, and that whole thing would have given you 3. Conceptually, I want you to understand because of what's coming here in just a bit, okay? Are we good? Okay, so let's do direct substitution, and let's do this example right here. If I directly substituted this right here, what I'm really looking at is what is the cosine of 5 pi over 6? You with me? So the cosine of 5 pi over 6, I'm not going to draw the graph, but I will draw you the unit circle that I hope you have memorized. At 5 pi over 6, which is right here, do y'all remember what the xy value is there? Awesome, guys. Awesome. And the cosine is talking about which one of those? The x. Sine is y. What's tangent? Y over x. Perfect. So this is just going to be, and you're done. You with me? Yes?
Can you do direct substitution for all of these?
That's the question. That would be nice, right? If you could do direct substitution, it would be like so easy, right? The answer is yes. But here's the thing. Most of the answers are going to be undefined unless you algebraically manipulate. And we're going to do that on the next slide. Not just yet. And that's where the work comes in. That's what makes our first test a total non-calculator, because we're having to do all the work by hand. Okay? That's a really, really good question that she just said. Alright, so listen. Let's directly substitute this in for x. 7 pi over 4. Okay? This is 1 pi over 4, 2 pi over 4, 3 pi over 4. This is 4 pi over 4 because I know that this cancels to a form of what? 1. So you'd be left with pi. You keep going, 5, 6, and 7 pi over 4. Remember, these are at the 45s. So this is root 2 over 2 and negative root 2 over 2. A positive x and a negative y. Okay? Y'all said it before. Tangent is y divided by x. That's not a y. So a y divided by x, if I'm looking at my unit circle, would be that value right here divided by the x. And what I'm about to show you will help you a lot in all the algebra that's about to come your way, okay? Y over x is this. It's negative 1. Some of you see it just like that. What I want you to do, couple things. These won't always be the same, okay? When they're different, what I would like for you to do is to read this as this, the way you did it in 5th grade. Negative root 2 over 2 divided by root 2 over 2. Because in 5th grade what you learned was keep, change, and then flip. And what have I been telling you you want to do as early as possible when you're multiplying? You want to what? Cancel, right? You want to cancel and reduce as much as you can to forms of 1 if you can. So 2 over 2 will reduce to 1. Root 2 over root 2 is reducing to 1. Nonetheless, the answer is negative 1. We good? Alright, a couple more things. At these 45s, this is creating y equals x. Okay? At these 45s, what is this equation? Negative x. Can someone tell me the slope here? 1. How about the slope here? Negative 1. If you haven't learned it by now, guys, tangent is slope. So when you're doing this, when you're doing tangent, if you're at the 45s, here or here, it's going to be an answer of a -1. If it's here or here, what's the answer if it's tangent? 1. How about here? What's the tangent, aka slope of that line? 0. Okay? And what is the slope of this line? Undefined. Nicely done. So listen, if I said the tangent here, what do you say? Undefined. But what if I say the limit there? What would you say? Does not exist. Okay, one more thing before we move on to the next slide. Could I have brought in, rewriting, could I have brought in this limit inside like that? That's limit law number 7. Could I have brought that limit inside to do with 7x first? Yes or no? No. Because the most outer function is not what? Continuous. Okay? If you recall back from pre-cal, the tangent function was like this, with a bunch of vertical asymptotes that existed in between. Okay? I know that's a lot of stuff. Any questions? Okay. So here we go. So the question that was asked was, do we always directly substitute? And the answer is, you should always try that first. But sometimes, in fact very frequently, you're not going to be able to get an answer that way. Because then you'd have a bunch of does not exist answers. Okay? You have to do this. You have to do algebraic manipulation in order to get an answer.
Wait, so if you're saying that direct substitution will get us a bunch of doesn't exist answers, does that mean if we get does not exist, it might be wrong?
Yes. Did you hear that? If you get something that does not exist, chances are when you are first starting calculus, it might not be does not exist. There'll be another answer. You just didn't do the proper algebraic techniques in order to get to that answer. Go with me? For instance, let's look at this one. If we directly substituted -3 everywhere where we saw an x, what would I have in the numerator? 0. What would I have in the denominator? 0. I have a 0 over 0 form. Because of this, I might need to do some extra work to see, this number might actually be something else. It might actually be like 5. The answer might be 10. I have to do this to see what Christian just asked, or is there an answer to this? You with me, guys? Now, I'm going to tie it to something very, very basic. Listen. So let's look at this right here. And if I ask you to tell me, guys, this is a domain. And I want you to give me an inequality to describe that domain right here. What would you say? X is greater than -1. Raise your hand if you would have said that. Okay? Who would have said something different? So I saw all of y'all's hands go up on that one. Would you agree that this could also be this? Right? Some of you are like kind of shrugging the shoulders a little bit. Yeah, because it feels weird. This to me doesn't feel as comfortable and confident as this. And what we're learning today, to start off today, and we're going to be doing this for a while, is rewrite sometimes does not feel comfortable. But all the rewrite and the manipulations that we're going to do will get to our answer that we're looking for. Are y'all with me? Okay. So listen. Let me get rid of this. And I'm going to ask you. By direct substitution, you guys have really awesome questions, for sure. By direct substitution, the bottom piece is what makes this undefined, preemptively. So what's our goal? Our goal is to cancel that bottom piece some way or somehow, if we can. You with me? So our bottom piece is x plus 3. Our goal is to cancel this altogether. Here we go. Our first thing that we learned in Algebra 2 was factoring quadratics like you have in your numerator. Let's factor this right here, guys. What are the factors? X plus 3, x minus 2. Make sure that you're doing this each line. Yours will be vertical, like you'll have vertical work, and then when you finish and you run out of room, draw an arrow and you'll have vertical work. But for the sake of instruction, I'm going to do it horizontally, okay? Alright, so here we go. This right here is what we've started to algebraically manipulate it to. Let me ask you this. Can someone tell me without using a calculator what they think this is actually going to look like? What kind of function, by looking at the original one, do you think it could possibly look like? Think of parent functions. The top is a quadratic. We know those look like parabolas. Say again? Rational. So it also looks like a rational function, which is 1 over x. You with me? But the thing is, it's neither of these.
X minus 2?
Yeah, it's just x minus 2. Because look at this. The graph is actually going to be x minus 2 with a whole, where? Negative 3. This is why we learned that pre-cal graphing by hand business stuff. So at negative 3, we'll go down to the graph, and we're going to create a hole right here, and everything else is graphed. Because what were we able to do before we plugged in our limit? We were able to cancel our piece to a form of what? 1. Guys, you're going to hear me say this a lot. Cancel, reduce as early as possible. Simplify as early as possible. Look to see, where can I cancel multiplication to forms of 1? Listen to me carefully. What if I cancel to forms of addition and subtraction? What do forms of adding and subtracting numbers cancel to? 0. So we have cancellations of 0, we have cancellations of 1. Okay? Now, let's approach negative 3 from the right and from the left on the graph. Can someone tell me what would that answer give me? Negative 5. So all of this is negative 5. Because, real quick, because remember, the limit is what the y value wants to be, not what it is. And if you get infinitely close, right here, to negative 3, from the right and from the left, and you get infinitely close, remember, like the hot iron to the face example that we did on day 1, we didn't have to actually touch it for the limit to exist. We just have to get infinitely close, and that limit that you feel, that's the limit. Yes?
How could it be a rational?
It's not either one of these. So, it's not either one of these. I just wanted you to tell me, what do you think it was looking like at first glance? Just so that you could see with algebraic manipulation, what it truly is just a linear function that's shifted down to. Cool? Alright, questions? Alright, so let's go. So here's the thing. Once you cancel the piece that otherwise would have made it undefined, do y'all know that saying, hey, you just won the Super Bowl, what are you going to do next? What do they usually say after that?
Going to Disney World.
I'm going to Disney World or going to Disneyland. So yours is, you just canceled the piece that would have made this undefined. What are you going to do next?
Disneyland.
No, don't go to Disneyland. You're going to plug in your limit. You're going to plug in that C value and get your answer. I know that's not as fun, but
Pretty fun.
that's your second step. Alright, so let's move on to the next one. Guys, that's one of many algebraic manipulations. What we just did is what makes calculus, quote unquote, difficult. It's not the calculus, it's the algebra 2 that you're doing to manipulate and rewrite that makes it difficult. Okay? So please, make sure that you understand that it's just algebra 2 all over again in a lot of ways. In a lot of ways. Our second example. Okay, our second example. What is our goal? First, we always do what first? Direct substitution. If I plug in directly, what's the top? 0. What's the bottom? 0. Which one of these tells me I might have to try something? The denominator, because we can't divide by 0. Okay, here we go. How can we manipulate this equation in a way that we could end up canceling the x minus 4 at the end? Squaring, that's a good suggestion, but it's not squaring. You're close.
By x plus 4 over x plus 4.
So he's getting close. You see, now he said first squaring something. Then he said let's multiply by a form of 1. But you're not going to get rid of it. On the bottom, you're just going to end up having this.
X plus 3, or x minus 3.
So some people might go for the x minus 3. And here's the thing. You're going to probably think this a lot as we go through this and throughout the year, is how do you know to do that? How do you know to manipulate it that way? And it's just from practice and experience. Practice and experience. And when you build that, you will learn what you should do, okay? But it needs more experience. Here we go. Something that you learned probably in Algebra 2. Did I multiply by a form of 1? Yes or no?
Yes.
Yes. What is this form of 1 called?
It's the conjugate.
Nice, the conjugate. So the conjugate, if you didn't learn this way back when, you can learn it now, is why the conjugate? Your goal is to get rid of this in the numerator. Now let's think about this. You've been used to doing this. You've been used to seeing, you can't have a radical in the denominator. You have to rationalize. So if we multiply by a form of 1, when I multiply these two together, what do I get? 2. Multiply the numerator together, I get 2 root 2. And at the end, I will be able to reduce so that my final answer is this. It went from this original to that. Why? Because I learned how to rationalize the denominator. Because now it's over and understood what? 1. So this one feels like that, but we're not trying to get rid of the denominator. We're trying to get rid of this numerator square root piece. Here we go. Look carefully. All of this is one piece. All of the top here is one piece. Just like bottom here is one piece, all of this is one piece. 3 words. I'm thinking of 3 words that when I multiply these two, it represents something that we did way back in Algebra 2. What are the 3 words? Difference of squares. So, yes, you could FOIL this out if you wanted to. Or, so let's do FOIL. So the first What will that become when I FOIL that out? X minus 3. Guys, I will say this all year. The number one mistake in calculus is you're missing it by a negative. And if you miss it by a negative in step 2, at the very final answer, you're way off. Okay? The second most common mistake is people don't show enough parentheses. If you don't show enough parentheses, your algebra 2 is going to be wrong, and it makes the entire problem wrong. Notice what I just did. I squared this, but I left the parentheses. Because sometimes there could be a number left in front that it's very important tied to that you want to make sure that you're good to go on. So, what's the rest of this? If I were to FOIL this out, look at this very carefully. The outside is a positive root of x minus 3. The inside is a what? Negative. Difference of squares, those outside and inside terms will add up and cancel to what always? 0. Okay? So what's left is a minus 1. Okay? You're going to ask, how did you know to do the next step? And I'm going to tell you through experience. Don't ever distribute the denominator. Don't. Just leave it factored. Okay? So I'm going to leave it just like it was. But please tell me what is wrong with what I just wrote. I don't have parentheses, but I need them. So I'm going to put parentheses here and here. Do you see anything that we can cancel right now? X minus 4 over x minus 4. Look at the numerator. Simplify it before you move on. What's the numerator simplified to? X minus 4. And if you need to, write it out. Because now, get this, you can create all of this as one piece that will cancel with this. And what you're left with is 1 over the square root of x minus 3 plus 1. And guys, you should have been writing a limit every single step of the way, like here, and then here. Keep writing it each time, because if you don't, you just change the limit into a function, which is not the same thing. We know that. Guys, what's the final answer? Well, wait. You just canceled the piece that would have made it undefined otherwise. What are you going to do next? Plug in the limit. What's the answer? 1/2. We didn't draw the picture, but if we did draw the picture, we still would have gotten to that 1/2. Why? Through algebraic manipulation. Alright, we'll do one more. And then we'll do our quiz. Our last one is this. Guys, this is a big one right here. Because this you're going to use the most, I think. And this is what you're going to struggle most whenever you're doing it by hand. I have this as my original equation. And what I'm going to do is I'm going to multiply the denominator or the numerator. So let's highlight the numerator in orange. All of this is the numerator. And notice this x down here, I just wrote it. We got to keep track of all our variables. We have to, attention to detail is about to go up crazily with math, okay? Now, what could I multiply this by, and what could I multiply this by, so that I have common denominators up top? 2 over 2, and x plus 2 over x plus 2. Because now our common denominator is that. Are we good? Alright. I told you never distribute denominators. So we're going to write that right here. And remember, it's all over x. This one right here. Let's see what we get when we distribute that. What would I write? What's the 2 times 1? 2. Just 2, right? Now let's distribute this. Be careful, because this mistake right here haunts people in calculus. This negative across parentheses, you got to be very careful how you do that. I would distribute the 1 first, so nothing changes. then I would distribute the negative. So I'm distributing this negative across something that looks like this. You with me? Alright. Let's simplify this before we start canceling. Now, someone asked me this earlier today during second period. Couldn't you just cancel these two?
No, because you're subtracting.
Because I'm subtracting the top. You can only cancel if multiplication exists here and here. But multiplication doesn't exist there. It's subtraction. So you can't cancel early. That's another thing that haunts people, is that they cancel at inappropriate times. So what am I going to do? I'm going to distribute this negative on both of them. So it'll become 2 minus x minus 2 over 2x plus 2 all over x. I told you, it's going to look ugly before it looks pretty. We are not distributing this, still the same, but could we simplify that? Yeah, the 2's go away to what number? 0. Cancellation of 0. So now, let's get rid of them. And if you're that type of person that needs to get rid of them, please do so. Christian, read that for me real quick.
Negative x.
A little bit louder.
Negative x over 2 times x plus 2 all over x.
All over x. All divided by x. Do you agree?
Yes.
Now, I would venture to say a lot of you might struggle with this, but if you go back to 5th grade and wrote it like this, it'll be easier. All that divided by x. Keep, change, flip. So divided by x is the same as multiplying by what? The reciprocal. Now you see that the x is going to line up with the 2x plus 2 on the bottom. So this x kind of will come up just one level and will end up looking like this when you simplify at the end. Again, because of the sake of time, we need to make sure we're doing this all the way. What exists here? Multiplication. What exists there? Multiplication. Can I cancel the x's now? Yes. The x that was looming at the very beginning, I can finally cancel to a form of what? To 1, right? Or negative 1 in this case. Whoops. You just canceled the piece that otherwise would make this undefined. What are you going to do next? Plug in your limit. What do you get? Negative 1/4.
So on the denominator, if it was x times and then that other value, like the 2x plus 2 or whatever, or 2 times x plus 2, if that was like an added value, could you still?
Here's what I'll say. The way it canceled pretty for us, if you do the numerator pieces correctly, you will be able to cancel this pretty. If it doesn't cancel pretty, chances are you did something wrong up here. Okay?
How did you get from second? Yeah, like there.
How did I get from here to here?
No,
From here to the one I drew over here?
no, like the one before that one. Like there.
The one with the green to the...
How did I get from this to that?
Yeah.
Okay, so the numerators multiplied together gave me this 2 right here. 1 multiplied with this gave me this. And all I'm doing...
It's the same denominator. Yeah.
Yeah. Do you see it? Yeah, the same denominator. Common denominator, I was able to bring them both together. Alright guys, go ahead and clear your desks.